Hello, everyone. Welcome to this week's Crunch seminar. Today we have two speakers. Our first speaker is Professor Jun Zhang, who is a professor at Beihang University and serves as the head of the Department of Machine and Environmental Engineering. He completed his PhD at the Institute of Mechanics in the Chinese Academy of Sciences in 2009. Following this, he gained professional experience at the Institute of Mechanics at the Chinese Academy of Science, as well as the University of Strathclyde at the University of Edinburgh in the UK. Zhang Jun returned to China and joined Beihang University in 2017, and his research focuses on multiscale simulation and data-driven modeling for non-equilibrium gas flows and gas surface interactions. He has published over 60 papers featured in top journals such as Journal of Fluid Mechanics, Journals of Computational Physics, and Physical Review. As the principal investigator, he has overseen 4 projects supported by the National Natural Science Foundation of China. Professor Jun, with this short introduction, the floor is yours, and whenever you're ready, you can start.
Okay, thank you. Thank you for the nice introduction. Thank Professor George Kaniadakis for providing me this chance to give my recent work. The title of my talk today is about multiscale particle simulation of non-equilibrium gas flows and data-driven discovery of governing equations. First, I will provide a very brief introduction to the background of my talk. As you know, now in many modern engineering problems, actually it's very crucial to efficiently and accurately simulate non-equilibrium gas flows, such as those occurring in microscale processor chips and hypersonic flights in the near space. Because my university is famous as aerospace engineering, so I take flight as an example. As the increase of the altitude, we know that the air density decreases, resulting the molecular mean free path increases from about 65 nanometer at the sea level to about 1 centimeter at 85 kilometer. Generally, we can use the non-dimensional collision number to identify whether a gas flow falls in the continuum or slip or transitional or free molecular regimes. By the way, the collision number is defined as the ratio of the molecular mean free path to the characteristic length. If the flow is in the continuum or slip regime, we can use the Navier-Stokes equation to describe it. However, if the flow goes to the transitional regime, the Navier-Stokes equation fails, and the Boltzmann equation is appropriate. Numerically, we can use the deterministic method, such as DVM method, or the stochastic method, such as the DSMC method, to solve the Boltzmann equation. So to enhance the computational efficiency and accuracy, there are 2 ways to work on. The first way is extend the particle method, like DSMC, into the continuum regime. And the second way is to extend the macroscopic governing equations, like NS equation, to the transitional regime. The latter is particularly relevant to data-driven modeling I will talk about. And the training data comes from the particle simulations. So in this talk, I will begin by discussing the particle simulation method from DSMC to multiscale particle method. DSMC actually is very simple. The idea is to track a large number of representative molecules and to calculate molecular movements and intermolecular conditions. And the macroscopic properties, such as velocity, temperature, are obtained by taking average of molecular information. There have been a lot of applications since it was proposed in 1960s. Here is one application of DSMC to the satellites in the very new Earth orbit, which now is a very hot research topic in aerospace engineering recently, as it can provide numerous benefits than traditional higher altitude satellites. Using DSMC, we can predict the aerodynamic properties, particularly the drag force of the VLEO, and then we can do some optimal design for drag reduction. Our DSMC simulation results demonstrated that we can use natural side smoothing or increase the aspect ratio can reduce the drag force significantly. Also, we can employ DSMC to study the spacecraft reentry problem. Generally, the DSMC results can be used as the standard to check the applicability of other simulation methods in the transitional regime. So far, DSMC has been widely used to calculate aerodynamic properties for high-speed flows with low density. However, it's very challenging to apply DSMC to three-dimensional gas flows in the near continuum regime. It's well known that there are two main challenges to limit the application of DSMC. The first is the small time step and the cell size. To address this issue, my collaborator, Professor Fei Fei, and me have developed a unified stochastic particle method. And I will discuss the recent advancement with the USP method and show some applications. The second issue is actually the statistical fluctuations, which can be particularly a big problem in low speed flows. To tackle this, we have recently extended the USP method into the denoising multiscale particle method, like DMP method. So I will go to the second part of my talk, multiscale particle simulation. As we know, actually the DSMC method is essentially a operator splitting particle method. It means that the molecular motions and the molecular conditions are uncoupled. It corresponds to the convection part of the Boltzmann equation and the condition part of the Boltzmann equation. So this treatment makes the implementation of DSMC very convenient. However, to ensure the numerical accuracy of DSMC, it requires that the cell size should be smaller than the molecular mean free path, and the time step should be less than the molecular condition time. Otherwise, the numerical transport coefficients would deviate the physical ones. These two requirements have been demonstrated by numerical experiments and theoretical analysis. So for the application of DSMC to the continuum flow, generally it needs huge computational resources, and sometimes it's inaccessible. Besides DSMC, there is another particle method referred to as a stochastic particle method, or SP for short. In SP method, actually the molecular motions is the same as DSMC, but the condition part is replaced by a relaxation process defined by the BGK model. And because the BGK model, we can have the analytical solution. So we know that for this model, we can actually replace the molecular conditions by the relaxation scheme. Just one part of molecules, we can keep the velocity, and the another part, we can sampling from the equilibrium distribution function. So using this relaxation process, we can improve the efficiency of condition, but the SP method has the same limitation as DSMC because it's still a splitting method, and it ignores condition effect during the motions. So the time step and the cell size has similar limitation as DSMC. So why does the operator splitting method generating numerical errors? These two figures provide a quantitative explanation. In these two figures, particles are color-coded to represent their local equilibrium state. We analyze the flux across the dot-dashed line. The left figure illustrates the physical reality. The particles have reached their local equilibrium state near the dot-dashed line due to numerous conditions before crossing it. In contrast, the right figure shows the scenario in the operator splitting method. Here, particles undergo free transport over a long distance and maintain their initial local equilibrium state when crossing the dot-dashed line. So, quantitatively, the flux of the velocity distribution function consists of two parts, one from the initial distribution function and another from the gradient of the distribution function. It's like showing in this figure. Similarly, the numerical stress and the heat flux is composed of two parts, the initial part and the gradient part. As seen, the gradient part is proposed to the time step, making the main source of numerical error in the splitting method. So the key idea of our proposed USP method is to design a specific model for condition and adjust the flux of the initial part accordingly. And then we can ensure that the total flux of both the initial part and the gradient part approach the Navier-Stokes flux with the second order accuracy in the continuum regime. Consequently, this approach allows to precisely determine the parameters in the designed distribution function in the USP method. And for the details, please refer to these two papers published in JCP this year and 2020. Here, I provide a brief summary of the implementation of the USP algorithm. It's similar to DSMC and includes four key steps: initialization and ballistic motion and USP type, velocity relaxation and sampling. Actually, besides the relaxation step, all other steps are the same as DSMC. In the relaxation step, we need to compute macroscopic properties, and then we can resample particle velocities in each cell based on the FUSP, and the distribution function is defined like this, and the parameters is proportional to time step. And then we can scale velocities for conservation of momentum and energy, and then we finish this step. This is the basic algorithm of the USP method. To do this, we can achieve second order of time step. Next, I will show some simple case of the.
Can I ask a question?
Okay.
So you have now second order accuracy, right? So which is on the flux and the stresses, but you still have the constraints in terms of time step and mean free path, right?
Yes, but now the numerical error is much smaller than DSMC. I will show some like cases. Yeah.
Sure. But I'm saying you cannot take arbitrary large time steps. You still have small time step.
No, actually now as you can see in this case, actually is a demonstration. This is a one-dimensional quality flow. As you can see, we can increase the time step. This is the time step divided by the molecular condition time. As you can see, for DSMC and SP, if you increase the time step, it's deviate the theoretical ones. This one is the numerical stress divided by the theoretical one. It's deviate if the time step increase. However, for our method, USP method, even the time step is 10 times of the molecular condition time. The numerical error is also very small. So this is like demonstration. But we know if the time step is much larger, and there are still numerical errors, but it's smaller than DSMC. It's like this maybe. Have I answered your question?
Yes, I mean, it looks like a big difference here because at the end is that all delta t versus all delta t square, but I know it also you denoise the DSMC, so that's a big difference. Yeah, you answered. Yeah, thank you.
Oh, okay. So I will continue my talk. This is the first case for one-dimensional gravity flow, and we also apply this method to two-dimensional flows. Like it's like in this model, it's like a competition of natural convection and thermal creep. And this figure is a schematic diagram of simulation model. The argon gas is confined in the square enclosure. The left wall has higher temperature than the right wall. And the two horizontal walls have linear temperature distribution from the low temperature to the higher temperature. In the continuum regime, our method predicts a natural convection, which is consistent with the traditional CFD results. And in the transitional regime, USP predicts a thermal creep phenomena, which is consistent with the DSMC result. And in the mediate regime of Knudsen number, USP predicts a mixed flow pattern. And to address more complex engineering problems, we have integrated the USP method into our open source code with the DSMC solver framework, Sparta. Sparta was originally developed by Sandian National Laboratory and is extensively used for simulation rarefied gas flows. By merging Sparta with the USP method, we have named our enhanced code Spacast. It's also open source, so you can download it freely. Using Sparta, we can simulate more complex flows. This is one three-dimensional flow around a re-entry vehicle simulated by Spacast. The Knudsen number is 0.01. The bottom half shows the temperature counters obtained by DSMC use the standard time step, and the top half shows the temperature counters obtained by USB using 50 times of the standard time step. As you can see, the result is consistent with the standard DSMC results. Also, we compare the heat flux on the windward side. The bottom half is also the DSMC standard result. If using DSMC with large time step, the predicted heat flux will deviate the standard method. However, if we use the large time step with USP, as you can see, the result actually is consistent with DSMC. And in this case, the computational efficiency is improved by more than 100 times compared to DSMC. So it's a big improvement. And we can also use Spacast to simulate turbulent flows. Here is a case we use USP to simulate 3D compressible decking isotropic turbulence with varying initial turbulent Mach numbers. Different from DNS based on Navier-Stokes equation, in USP simulations, actually it inherently incorporates thermal fluctuations arising from molecular thermal motions. So after eliminating thermal fluctuations, the USP results, as you can see, agree well with the DNS results. And more interestingly, we can compare.
Can you go back to this? I didn't have a chance to look at this slide.
Okay.
The previous one.
This one, yeah.
This one, yeah. So you compare with DNS. What DNS is that? Is that spectral DNS? What is it?
Actually, in this case, for let me check.
Because I see a lot of wiggles. That's not what DNS is. If you use Fourier, for example, if you use a Fourier here, it would be a very smooth.
Actually, this DNS is based on based on BGK solvent BGK equations. Actually, it's not based on Navier-Stokes equation.
Oh, okay. So it's Lattice-Boltzmann.
It's similar, but it's not exactly LBM. It's based on Shukun-Kunshi's scheme. It's like GKS.
But for example, the pressure fluctuations on the left, right? Are they supposed to have these wiggles, or it's a smooth curve?
Sorry?
You see the pressure, the mean square pressure fluctuations that you have in the middle.
Yes.
I see lots of wiggles. I see the peak is, and then the decay as a function of time. But it's not a smooth decay. Is that correct, or is it just artifact of the stochastic simulations and in the mean? Because this is the RMS, right? So you still took the average, but I see these fluctuations. Are they real, or because of the Mach number, or is it an incompressible flow? Incompressible decaying isotropic turbulence, incompressible will not have this. Will not look like this. Will look very smooth.
Yes, but I think in this case it's not numerical fluctuations. I think it's physical fluctuations, because the Mach number is around one. It's compressible flows. Yeah.
Okay. All right. Thank you.
Okay. So go on. And here we compare the energy spectra of the velocity field obtained from USP and DNS simulations at a given instant. It can be observed that in the low wave number regime range, the USP spectra are in good agreement with the DNS spectra. But in the high wave number range, unlike the DNS spectra, the USP spectra shows a K-square power law, which corresponds to the effect of thermal fluctuations. Actually, we can define the crossover wave number to represent the length scale below which the thermal fluctuations dominate the turbulent spectra. It's found that the critical length is comparable to the Kolmogorov length scale, and indicate that the thermal fluctuations will become significant if the scale is smaller than the Kolmogorov length. And this work has been published recently in JFM. So besides the USP method, we have also developed a multiscale stochastic particle method. We call it MSP method, based on the Fock-Planck model, or equivalently the non-given equation. By leveraging the exact solution of a non-given equation for homogeneous problem, we have extended it to inhomogeneous problem. Using a similar strategy to correct the numerical error from operator splitting, we have proposed the MSP method. which achieves second-order accuracy in time step as well. So this work is still under review in JCP. And to reduce the statistical noise inherent in particle simulations, we further develop a denoised multiscale particle method, DMP method, which is a combination of the MSP method and the information preservation method. In DMP, each simulation molecule has information velocity and information temperature in addition to molecular velocity. And the information velocity can be regarded as the connective velocity of a group of real molecules. And then the macroscopic flow velocity is determined by sampling the information velocity instead of the molecular velocity. It was shown that this sampling strategy resulted in a much lower statistical scatter than a typical DSMC simulation. So, and DMP simulation can save computation time by several orders of magnitude compared with a similar DSMC. Our latest work has built a rigorous theoretical framework for the DMP method. To achieve this, we introduce a velocity information joint distribution function, VIGDF, which is a function of molecular velocity, position, time, as well as information velocity and temperature. And based on VIGDF, we can derive the information augmented Boltzmann equation, and then we developed the denoised multiscale particle method. And this work is also submitted to JCP. So now I turn to the third part of my talk, is like data-driven discovery of governing equations. So first, I talk about the motivation of this work. It's known that the particle simulations, including our proposed multiscale particle method, although it can be applied to the continuum regime now, but they're still less efficient than directly solving macroscopic governing equations in the continuum regime. On the other hand, the conventional governing equations, such as the Navier-Stokes equation, are only valid in the continuum regime and the sleep regimes. So it's significant but very challenging to extend the macroscopic governing equations to the transitional regime. According to the kinetic theory, we know that macroscopic governing equations for gas flows can be derived from the Boltzmann equation. The Boltzmann equation is based on the molecular velocity distribution function. And there are two classical methods to derive the macroscopic governing equation based on the Boltzmann equation. One is called the grad moment method, and another is the Chambers-Enskog expansion method, CE expansion. The CE expansion expand the distribution function around the equilibrium state in a series of the Knudsen number. At the zeroth order of the Knudsen number, it goes to the Euler equations. To the first order, we can get the Navier-Stokes Fourier equations. And if we expand to the second order, we can get the Berlet equations. However, the practical application of the Berlet equation to highly non-equilibrium gas flows remain limited and unclear. And most of times, the Berlet equation is unstable, so it's difficult to be used. So therefore, using machine learning methods to derive governing equations for non-equilibrium gas flows is very intriguing. Indeed, there have been a variety of data-driven methods to derive the equations. In 2020, we combined the sparse regression and the data generated by the particle simulation to derive the macroscopic governing equations. And we know that in particle simulation, we don't need to assume any macroscopic governing equations or constitutive relations a priori. So they rely only on molecular models, and the macroscopic quantities are obtained by averaging molecular information. Once the data are prepared, the remaining task is to apply a data-driven algorithm. So the algorithm we used is the so-called sparse regression, and this is based on the work published by Professor Bruton and his team. Their two key papers address data-driven discovery of ODE and PDE, respectively. The fundamental idea behind sparse regression is to construct a library of candidate functions and then determine the coefficients of each candidate function from the data. The resulting equation is a linear combination of a few candidate functions with non-zero coefficients. Generally, sparse regression provides an explicit equation in the simplified form, as it aims to reduce the number of candidate functions. Next, I will present some simple cases we have worked on. The first case is just a one-dimensional shear flow with a gradient in the vertical direction. Since the horizontal direction is uniform, we do average, and then we get the data consist of 256 spatial cells in the vertical direction and 100 time steps. Based on the spatial temporal evolution of data, we can derive the governing equations, which is consistent with the theoretical ones, with only a minor numerical error in the viscosity coefficient. And we also simulate a similar problem, a diffusion problem, involving two species with a density gradient in the vertical direction. Similarly, we can derive the diffusion equation from the spatial temporal data generated by the particle simulation. And note that in the particle simulation, we can assess particle information, including their positions and velocities in real time. So it's intriguing to explore whether we can derive the governing equations based on the particle data instead of macroscopic quantities. To study this, we randomly select 100 representative particles from the simulation and record their positions. Using these data, we determine the particle displacements over various time intervals. We then obtain the probability density function of these displacements by averaging. With the probability density function as input data, we derive the governing equation, which aligns with the Fock-Planck equation without a convection term. And this case demonstrates that actually we can even discover the governing equations from the particle data. And the next case is a two-dimensional problem known as the Taylor-Green vertex. We derive the governing equations based on the data from the two-dimensional particle simulations, like this. At first glance, the derived equations appears to lack the two convective terms on the left-hand side compared to the theoretical vorticity transport equation. However, this does not indicate an error. Rather, the derived governing equation is just a simplified form specific to the Taylor-Green vertex problem. Because in this special case, the accurate input data causes the summation of the two convective terms to be very close to zero, leading to their automatic elimination in the derived governing equation. So this simplification is a result of sparse regression, which aims to find the most parsimonious form of the underlying governing equations. So interestingly, if we change the initial condition by doubling the number of vortices in the horizontal direction, we can then derive the full vorticity transport equation like this. And with only some numerical errors with the prefactors. So a very brief summary of the content covered in this part. We have preliminarily demonstrated that the feasibility of data-driven discovery of governing equations based on particle simulations. We use sparse regression, and it not only discovers the correct equation forms, but also provides accurate estimates of the transport coefficients. However, the disadvantage is that it requires a comprehensive candidate function library, and the expressive power and accuracy is limited. If we want to use sparse regression to discover unknown governing equations, so it's very challenging because maybe sometimes we don't know how to use the candidate function. So this is a big problem.
Jun, I have a question
Okay.
before you go to the next topic. Here it's not if you go to, like you said, finite Knudsen number, let's say 0.1, it's not just the governing equation, it's also the boundary conditions. So you may discover the equivalent, let's say, macroscopic equation for in the finite Knudsen number regime, but you also need to worry about boundary conditions. How would you discover the boundary conditions?
Actually, so far we haven't done this. So as you can see, in all the simulation cases, actually, this one is like a periodic boundary conditions.
I know, but you avoid the problem. But I'm saying that's the real problem. The problem is if you're in the mesoscopic Knudsen number around 0.1 to 1, right? It's really the boundary condition that is changing, and that's what you need to capture together with the governing equation. So here you avoid it by just putting periodicity, but this is just to write a paper, not to solve the problem.
You're right. So maybe the next step, if we want to get not only the governing equation and the boundary condition as well. So we need to do a model with boundaries, and maybe.
But Cindy can do that. Cindy can also do boundary conditions.
Maybe they can do it, but we avoid it because this one where makes the problems more complicated.
Okay. All right. Please proceed.
Okay, thank you for your question. So now I go to the last one is like a GEP based data-driven discovery. So what GEP is a gene expression program, which compares mathematical expression into chromosome. Each chromosome is composed of one or more genes. Here you can see a schematic of a gene. A gene consists of two parts, the head and the tail. The head includes symbols from the function set or terminal set. And while the tail only contains symbols from the terminal set. The function set comprises basic operators such as addition, subtraction, multiplication, and division. The terminal set includes elements that may appear in the target equations, such as conserved variables and physical constants. Starting with the first symbol of the gene as the root node, we can translate the gene into an expression tree, thereby deriving the corresponding mathematical expression. It's important to note that the final four symbols in the gene are not expressed. The gene, the region before these symbols is known as the open reading frame, ORF, which has a variable length. And the length of gene is the total length is fixed. And this mechanism prevents chromosome bloating. So GEP mimics the principle of natural evolution to evolve and discover the best equations for describing the training data through genetic inheritance and mutation. In our work published in 2022, we demonstrate that the GEP can effectively reproduce the results of sparse regression. Moreover, GEP does not require candidate functions. It only needs basic function operators and terminal elements and can combine them to obtain equations in any forms. So these characteristics make GEP more suitable for exploring unknown equations. However, it's hard to incorporate physical constants. And when the data is noisy, it tends to get overfitting and non-physical results. So generally, it's a common practice to normalize the data before inputting into a GEP algorithm. However, we believe that the dimensions are very crucial for preliminarily validating the derived equations. Therefore, we propose incorporating dimension data and adding a dimension verification process into the evolution of the original GEP. In other words, our approach inputs the constraint of dimensional homogeneity to ensure the validity of the equations. And the other steps are the same as the original GEP. And this work has been published in GFM this year. So now there are two key problems that need to be addressed: how to do dimensional homogeneity constraint. The first is enabling computers to perform dimensional calculations. The second is ensuring computational efficiency, as each gene must be checked for dimensional constancy during evolution. To tackle these issues, we propose aligning numeric tags to each symbol and replacing symbolic operations with numerical operations. Specifically, we use prime number tags for base dimensions and the numeric tags for other derived variables that can be determined accordingly. For instance, the dimension of speed is represented as length divided by time. So its corresponding numeric tag is 2 divided by 5. In the gene's expression tree, we calculate the numeric tags of each node from the bottom up. By comparing the numeric tag of the root node with that of the target variable, we can determine if the gene satisfies dimensional homogeneity. Additionally, the code for DHC GEP is now available on GitHub. You can also download it. So we first use this algorithm to check the performance of GEP with the original GEP using a cylinder flow data without any noise. Both methods were able to, as you can see, both methods are able to discover the correct equation. However, in the original GEP, the correctness is somewhat limited. From a data fitting perspective, the original GEP found the equation with the correct form and identified the viscosity coefficient as 0.01, which matches the real viscosity coefficient. However, it did not uncover the true underlying physical mechanism. When apply this equation to another case with different viscosity coefficient, this equation will be failed. On the other hand, for the discovered equation by DHC GEP, as you can see, here we can identify as the viscosity coefficient exactly. This is a big advantage of DHC GEP. So next, we tested the methods using noise data of cylinder flow. We found that DHC GEP was still able to discover the correct equation, whereas the original GEP cannot. Actually, the original GEP converted to a numerically accurate but incorrect equation, indicating of overfitting. It's also worth noting that in this case, we only use 400 training data in DHC-GP. But if we use sparse regression, we need like 200,000 training data. So for DHC-GP, we can use smaller data. For summary, for this benchmark studies, we can say that DHC-GP does not require assuming the function form in advance, and compared to original GP and DHC-GP years equations that better reveal the true physical mechanism, and DHC-GP are more robust to the level of data noise, data size, and model hyperparameters. And then we can, I will discuss two cases where we aim to uncover the unknown, the constitutive relation for non-equilibrium flows. The first case, we examine the one-dimensional shock wave, where the NS constitutive relation proves inadequate. High-order momentum equations, such as the Bernoulli equations, offer moderate accurate, but suffer from poor mathematical properties. For this case, when selecting terminal sets in the DHC-GP algorithm, we consider some key aspects. First, the constitutive relation describes the transport properties of local momentum and energy. So we select the local Knudsen number in the terminal set. And second, since the transport of momentum and energy is driven by gradient of macroscopic quantities, so we incorporate gradient terms into the terminal set. And third, local macroscopic quantities are crucial parameters. We select temperature and density as terminal elements, omitting velocity to ensure Gaussian invariance. In this context, velocity terms should not appear outside the partial differential operators. And lastly, we know that gas physical property parameters are also important. So we add the local viscosity coefficient, thermal conductivity coefficient, and specific heat ratio and the viscosity index to the terminal set. Furthermore, we introduce the constraint of the second law of thermodynamics. Theoretically, we can determine whether the constitutive equation satisfies the second law of thermodynamics using Clausius inequality. Here, the last two terms represent entropy production. The second law of thermodynamics requires that the total entropy production must be non-negative. So for heat flux, the entropy production term takes a specific form like this. To ensure compliance with the second law, we add a penalty term for this entropy production to the loss function. Specifically, we calculate the entropy production at each data point and count the number of points with negative entropy production. This count is then embedded into the loss function. A weight factor is denoted as alpha, controls the importance of this thermodynamic constraint. With these settings, we derived the constitutive equation using data from Mach number equals to 3 and 4. The resulting equation closely resembling Fourier laws of thermoconductivity, but include a correction term related to the local Knudsen number, like this. Next, we assess the validity of the data-driven equation. The following graphs display the heat flux calculated by various equations at different flow Mach number. The red dashed line represents the results obtained by DHC-GP, while the black circles indicate the results from DSMC. It's evident that the equations derived from DHC-GP outperform other equations, including the NS and Bernoulli equations. And additionally, we defined a relative error to further analyze the accuracy. As you can see, the error of DHC-GEP is significantly smaller than that of other equations. Notably, our training data consists of Mach number from 3 and 4. And as shown in this table, the equation derived from DHC-GEP is applicable not only within the interpolation region, but also beyond the training data, demonstrating the impressive generalization performance. And we further implemented the obtained constitutive relation from DHC-GEP into a self-dissolver and numerically solved the shockwave case. The results show that a high-level agreement between the CFD results with DHC-GEP relation and the results from DSMC. But as you can see, the results from NSF equation is significantly deviate from DSMC result. So this is the advantage of the date-driven constitutive relations. We also discovered the constitutive relation for the rarefied Poisson flow. In this case, the selection of terminal set is similar to that in the shockwave case, but we removed the high-order gradient terms, keeping only the first-order terms for simplification. And based on the data of DSMC with global close number of 0.01, 0.3, and 0.4, we obtained the equation like this. This is the constitutive relation for shear stress. In these figures, we compare the results from the constitutive relation from DHC-GEP and from the data DSMC. And as you can see, it's agree well with DSMC result, but for other equations, they failed. And here is our quantitative analysis of these equations. As you can see, the equation from DHC-GEP outperform other equations as well. So we can also prove this equation satisfies Gaussian invariance and the second law of thermodynamics using the same method as before. Moreover, we can demonstrate that this equation can be reduced to NS equation in the continuum regime. So I skip the detail here, and for more details, you can refer to the paper published in GFM as well. And I want to mention that, and this constitutive relation is very simple. So we require the same boundary conditions as NSF, and is linearly stable. So it's very convenient to be used. Now it's the concluding remarks for my talk. To break through the limitation of cell size and time step in DSMC, we developed the unified stochastic particle method, the USP method, and the open source Spacast solver, which has been applied to a variety of multiscale non-equilibrium gas flows. We also developed MSP and DMP methods, and their ongoing work. And second, we employed this. Okay, I just escaped this. And thirdly, we can combine the particle simulation with machine learning. We can discover some equations from the particle data, from the macroscopic data, based on the average of the molecular informations. And we can even try to use this strategy to discover unknown macroscopic governing equations, but it also presents some critical challenges. And here I list all the papers I mentioned before. If you are interested, you can read, and for more details. And finally, I want to say thanks to my collaborators and especially to postgraduates in my group, Feng Kaikai, Cui Ziqi, Yang Hao, Ma Qihan, Ma Wenjun, and many students. Thank you for your listening. Now we can have some questions and comments. Thank you.
Thank you so much, Jun. This was a wonderful talk. Thank you so much for sharing your work. Do we have any questions from the audience?
Maybe Raj, you have any questions on the?
I was just hi, Professor. This is Raj from Brown. So how your GP algorithm is different than symbolic regression? Like there also you have an operator and there also you have terminals, right? So
sorry, can you repeat your question?
Yeah, so the GEP algorithm which you proposed, how it is different than symbolic regression?
Yes, I go back to the
slide number 31, I think.
He's not proposing GP. GP exists. He's proposing the dimensional version of that.
Yes.
How you can put tags with the dimensionality, because so he has basically, I think what he's trying to do is to have dimensional consistency.
Yes.
Okay.
And that but did you try, Jun, did you try other symbolic regressors like GP-learn, for example, PySR and so on? Did you try this?
Not yet. Actually, there are. I know there are like a variety of symbolic regression methods. I have only tried GP. So the GP algorithm actually is the same as before. We only added dimensional constraint. Yeah. But the idea, I think the idea can be implemented to other symbolic regression methods. It's similar. I know that there are some papers published in Nature Communications or other journals. There are the same idea, like how to input the dimensional constraint to the algorithm.
Right, that's the paper by Wickham Liu. I know what you're talking about, the dimensional consistency, the pi theorem.
Yes, exactly.
Yeah, but I mean like for example, Raj and other people here are using PySR, PYSR, which is do you know the details, Raj? Like compared to this GEP, for example, where they have the head and the tail and they go the three.
It's a similar actually, because the function set, what they call it here, that is called the library of the functions, binary and unary operator, and the terminals are variables. So,
but what's the difference? What's the difference? What is you know the work that Miles did? What did he do different than GEP?
The same, I think. Both are same actually. Miles, the only thing Miles thesis is that he divide entire population in small population and do the fitness locally, and then they update it globally. So that is the one change, because rather than doing one set of binary expression with the same amount of the data, he splits it and he calls it different island of the data. So it's just in terms of efficiency, he has done it. But I think if this is a GAP algorithm, it's similar, like the underlying concept is similar actually.
Okay, so I just actually asked that question on Google, and it says that the major possible upside is that PySR is heavily optimized. It might give us some free speed ups by just switching back end into GEP.
Yes.
So it is an optimized version of GEP apparently. So that's why
at code level. At code level. Yeah, at code level, not at algorithm wise, it's almost same. So
Yeah, so June, my suggestion is to look at that PySR, because other people, the post I just looked at comes from electric circuits, and they have the
Okay.
the same question I pose. You can change, apparently you can change the GEP, the back end of GEP, and you can have different optimized versions.
Okay.
So PySR that's what they were discussing.
It's a good suggestion. Actually, when we did this work, actually we don't know the paper, the pi theory, how to do that. We do it separately, but after we submit our paper, we found, oh, there is a good work.
Yeah, your work is very good too. Good.
Thank you.
Publications. The question is still that, so because in the flows that you're looking at, which are the rarefied flows,
yes,
it's not sufficient to get the governing equations, because the boundary conditions change continuously with the Mach number, which affects the Knudsen number. So you cannot say I found the governing equations unless you find the proper conditions. We have in my book on microfluidics, actually, we have a second order slip boundary condition, second order with respect to Knudsen number, which is like a Padé approximation of an asymptotic expansion. So that boundary condition is good up to Knudsen number of order 1. So, but it has some parameters. Usually we fit it. It has a couple of parameters. So we fit the 2 parameters. So you can start with that boundary condition, and then through the data you can actually find the constants. So we have a book on microflows and nanoflows. In one of the chapters, we're talking about this Padé approximation to slip boundary condition up to Knudsen number 1, which is, of course, the transition regime. After that, it's free molecular and it's easier. But that from point 1 to 1, Knudsen number is very difficult. And so unless you're capturing simultaneously the boundary conditions, then you're missing half of the fun, because the fun, you cannot have thermal creep unless you change the boundary conditions. You talked about thermal creep. You cannot have thermal creep unless you talk about unless you have, I
agree.
Yeah. So these are the paper. It's a book by me and Beskok and Aluru.
Yeah. So for a practical application, so now our work is not complete. We need not only the governing equation in the internal flow, and we need also good boundary conditions. After we combine that, we can use it for a practical application. Yeah, maybe this is the next step for our work. Yeah.
But if you look at it from a molecular point of view, the boundary condition actually is not local. It's actually it's non-local in rarefied flows. The boundary condition, because you can look at from molecular dynamics, and you look at the potentials and so on. And you see you have to modify the potential as a function of distance from the wall to have the right boundary condition. You don't just modify the boundary condition. So when you go to rarefied flows, when the continuum breaks down, you have non-local interactions, which basically translate into having a potential of the particles interacting with the wall, which is totally different. And that layer is very important. So what I'm saying is you have to simultaneously find. You cannot find governing equations and then let me also find the boundary.
Yeah.
Not
I
like
agree.
that.
Yeah, I agree. Yeah.
Do we have any other questions? It looks like we do not, and we have a second speaker too. So, Dr. Jun, thank you so much for your time today. This was a really nice talk. Thank you for sharing your research with us. And
thank you.
Okay.
So now I stop the sharing.
Yes, please.
Okay, thank you.
We have a second talk, so please feel free to stay if you want. But also I know that it may be later, so thank you so much for being. It's almost 1 a.m. there, right? Okay.
Thank you.
Okay. Hi, Nicola. Can you hear me?
Hi, Juan. Yes, I can hear you. Yeah, can hear you very well. Actually, Dennis will, which is also online, will start, and we will split the presentation in two if it's okay.
Hey, Juan.
Okay, that's good. Hi, Dennis. Let me allow you to share your screen in that case. Dennis. Can you please try sharing your screen now?
Yes, let me see if I can do it. Okay. Zoom, iPad.
Great.
Right. Can you hear my voice and see the screen?
Yes. It looks nice.
Excellent.
Now let me introduce you to our audience, and then we can start. Okay.
Mm-hmm.
Okay. Well, I got the. Okay. Nicola Borri is an associate professor of finance in the Department of Economics and Finance at Louis University in Rome. Nicola joined the faculty at Louis in 2009 after completing his PhD in economics. In economics at Boston University. Nicola also holds a bachelor and master's in economics from Bocconi University, Milan. Nicola's research are primarily at the intersection of finance and macroeconomic, with a focus on quantitative asset pricing and vintage. Nicola is an associate editor at Economics Letters. Some of his recent papers appear in the Review of Asset Pricing Studies, Journal of Banking and Finance, Review of Economic Dynamics, and Journal of Empirical Finance. I'm trying to look, but I don't. Did you guys send me the bio for Denise? I didn't see it.
It's fine.
Yeah, I did, but anyway, I did send it, but anyway, it's fine.
Maybe Nicola can introduce Dennis.
Well,
Okay.
Okay.
Dennis is a professor at the UCLA, and he's gonna start presenting our work. I think that we can start, with the meat. Okay.
Yeah, basically, like we have this paper with 4 authors, Nicola and Jun from finance department, myself and Oleg from economics department. So I am from UCLA, Oleg is from Yale, Nicola is Louis at Rome, and Jun is from Rochester. Yeah, can we start?
Yes, please.
Okay,
thank you so
excellent.
much.
How much, Juan? How much time do we have? Like till 2, right?
It's usually 1 hour from now on, but
yeah,
if you
good.
need a few more minutes, it works.
No, I typically think it's a very bad idea to take more time from people than you expected to, so we're not going to do it. Anyway, so thanks for having us. It's a big pleasure to be here and present. Thanks for joining. I actually heard the end of the last conversation. I should say it's extremely exciting. So yeah, it's all great. And so yes, together with Nicola, we are going to talk about our paper called Implementable Kolmogorov-Arnold Architecture, one factor to bind the cross-section of returns. I already introduced the other authors of the paper, so that's fine. And so I guess in a nutshell, I think our paper is the first empirical application of Kolmogorov-Arnold representation. So we apply it to finance data on returns of various assets, such as stocks and equities. And we show that all the factors governing the dynamics of these returns through the Kolmogorov-Arnold theorem can be summarized into just one factor. And we develop a Kolmogorov-Arnold based estimator of this factor, and we show that the estimator outperforms other state-of-the-art finance methods. Okay, so I'll get to the finance part, of course, but the first thing I want to mention the Kolmogorov-Arnold representation theorem itself. It's a very cool theorem. It has many versions. The original version was formulated in Kolmogorov 57 paper through competition and collaboration with his student Arnold. So the two authors eventually on the paper. And the theorem is basically about showing that any multivariate continuous function can be decomposed into univariate continuous functions, which are combined through the operation of summation only. Okay, so that's what we have. We have any function, you take any continuous function f with d arguments. Let's say that each argument is taking values between 0 and 1. So for no matter what function f you take, you can find univariate continuous functions, this gq guy and psi pq guy, so that the original function can be written in this form. Okay, so you can see that we have here 2d plus 1 basically gq functions, and then 2d plus 1 times d psi pq functions. So it's actually a lot of function if dimension d is large, but the good thing is that they're all univariate. Like I said, the theorem attracted a lot of attention, and several versions of this Kolmogorov-Arnold representation appeared, but the one we are going to use is based on this paper by Schmidt-Hieber 2021. So what Schmidt-Hieber shows is that there exists a monotone function phi, which does not depend on the function f actually. So it just exists. You can take this function phi such that no matter what function f with d arguments you take, you can find another univariate function g such that this multivariate function f can be represented in this form. So only two functions, g and phi. Phi is universal and g is f dependent. But the thing is that g is continuous and phi is monotone. If you have seen the Arnold paper 57.1, this representation in Schmidt-Hieber might look confusing to you actually, because there is like a negative result in Arnold paper that says that there do exist continuous functions of just two arguments that cannot be represented in such a form. So it's weird, but the thing is that Arnold was thinking about the case where both g and phi are continuous. And in Schmidt-Hieber, only g is continuous, phi is monotone. So there is no contradiction, it's all good. So this is the version that we are going to use. But for the purposes like of notation, I'm also going to use the concept of Kolmogorov-Arnold architecture. For that, I will say that any function of this type, it has Kolmogorov-Arnold architecture. So basically, yes, this is it. And so in this language, a Kolmogorov-Arnold representation theorem says that any continuous function can be represented by a function with a Kolmogorov-Arnold architecture. It's clear where the notation architecture is coming from. It's coming from neural network literature. Okay, now we have this representation theorem. It's all cool, but whenever I'm talking to my colleagues and I mention this theorem, everyone is confused because, like, well, it seems like we are beating curse of dimensionality here. We like all know without any conditions, you cannot really like overcome curse of dimensionality. And by the way, by curse of dimensionality, I mean, roughly speaking, that the complexity of estimating a function with d arguments is increasing exponentially with the dimension d. But here, we just have a bunch of univariate functions, which are very easy to estimate. So we are beating curse of dimensionality, but there's a catch. The catch is that the function g is not particularly smooth. Okay, so we know it is continuous, but it's still highly irregular in general. Function phi is fine, it's just monotone, so it cannot be of high complexity, but g, that's a problematic one. But we'll get to that point later. Now, just speaking a little bit about the history of Kolmogorov-Arnold representation, I'm going to talk about Ka representation because, I mean, it's like it's a pleasure to pronounce Kolmogorov-Arnold, but it's just kind of hard, so I just say Ka representation. The original formulation, as I said, is due to Kolmogorov 57 and Arnold. For a long time, people were excited about this thing. It's very unexpected, but they didn't know what to do about it. And then in '87, Gert Nielsen, who is a computer scientist from UC San Diego, wrote a very short paper, just 3 pages, like no theorems, no nothing, no proofs, no simulations, nothing. But he made the point that, well, this Ka architecture is basically a neural network. So that means that Kolmogorov-Arnold representation has to be useful for the neural network literature. But shortly after that, Girossi and Tommaso Poggio wrote another paper, essentially another 3 pages, where they claimed that Ka representation is irrelevant. Essentially, it's no good because, and why is that? Well, because the functions appear in this univariate functions, they're super irregular. They're so bad, it's impossible to estimate them, it's impossible to use them, so we cannot really do anything with this representation. But then 2 years later, Kurkova, 1991, they wrote another paper. Now she claims that Ka architecture is relevant, and what she meant by that is that, okay, so maybe the original functions, if you want the exact representation, the functions are super irregular and non-smooth. But if you plug in some smooth functions, you can still provide a good approximation to the original continuous function. Okay, and at this step, we are really talking about Ka architecture. So Ka architectures with smooth functions still provide good approximations to continuous functions. That was her point. And then this Schmidt-Hibert 21 paper that I mentioned before, that's basically a very quantitative version of Kurkova claims. So Schmidt-Hibert derived approximation theory, like bounds for the approximation of continuous functions by multi-layer neural networks, multi-layer perceptrons via this Kolmogorov-Arnold architecture. And then there's one paper which seems to be like totally unnoticed in this literature, is due to Horowitz and Mum in 2007. That's also statistics publication. So I think that paper was really ahead of time because they actually considered a multi-layer Ka architecture. And what I mean by that is that in the original formulation, you see there are basically 2 layers, 1 and 2. But Horowitz and Mamen considered multi-layers. They were not interested in any applications in like approximation properties of such architectures. They were just about deriving the rate of convergence with which we can estimate such architecture. So it's a statistical paper eventually. But it's cool that already in 2007, they were considering multi-layer architectures, Ka architectures.
Dennis, can I, this is an excellent review actually, and I didn't know about the paper of Horowitz and Mamen. That makes a lot of sense. But since I talked to Poggio, to Tommaso Poggio, 10 days ago at MIT, and I asked him about this, and of course in 2016, there's another paper by Maskar and Poggio that they use the Kolmogorov representation to show that certain neural networks, for example, the deep neural networks, which is like a binary tree, basically, certain architecture, you beat the curse of dimensionality. So that I think that's one of the first papers that rigorously shows that using the Kolmogorov theorem, they show that they can beat the curse of dimensionality because you have, with a finite finite representation. That's a Maskar and Poggio, 20 years ago.
Yes, we can trace that, of course. It's very fun to beating curse of dimensionality. There must be some assumptions, like in general.
Yeah, the structure is a binary. It's a binary, structure of the
If you look at Schmidt-Hibert, for example, it's a very quantitative paper. He actually describe the order of Lipschitz continuity of this function G. And it basically decreases very fast with the dimension D. So like either way, either you're estimating a D-dimensional object or one-dimensional object whose order of continuity is like 1 over D, that's pretty much the same stuff. So he doesn't beat curse of dimensionality. But thanks for the reference. It's we are thinking a lot about what to do with this curse of dimensionality stuff. I mean, like all machine learning folks are thinking about it. So we definitely need to check out this Masker-Podger paper. Thanks. Yeah. And thanks for the question, for the point. Actually, if you have more, like, let us know immediately. I'm always happy to learn more stuff. Okay. Okay, so there's a lot of discussion whether it's like useful in theory, but like we think the big question is whether KA architecture is useful in practice. Okay, so does it work in empirical applications on real data? Apart from the theory. So after all, eventually, yes, it's nicer to have an architecture that can approximate any continuous function, but I don't care about like all continuous functions. I only care about the function in my particular application. And I want to approximate that particular function by KA architecture. That becomes a very empirical question. And so the answer has to be empirical as well. And so that's what we do in our paper. We apply the architecture on a very concrete, super complicated finance data set, and it shows it does work. After all, eventually, if you think about it, so people say that these Kolmogorov-Arnold functions, they're super regular, but that only happens on like a very fine resolution. So, okay, you cannot estimate them on a very fine resolution, but maybe you don't care about that fine resolution. Maybe like just getting like some coarse, like global, you only want to get like global features of those functions. Those could be quite regular and can be estimated. Who knows? It's an empirical question. And by the way, here's a famous quote from John von Neumann. With 4 parameters, we can fit an elephant. With 5, we can make him wiggle his trunk. So incidentally, in our paper, we also use 5 parameters. So it does work for our purposes. Okay. So yes, now we are getting to an empirical question, whether it works. And so we wrote this paper with Nicola, Jun, and Oleg, which we posted on arXiv this year on April 11, where we apply the KA architecture to finance data. We show that it suffices to have just one layer to outperform state-of-the-art methods in finance. And for this external Kolmogorov-Arnold function, it suffices to approximate it by 4th order polynomial. I think it's not the order, it's degree actually, 4th degree polynomial. And we also develop statistical theory like convergence rate, how good we can estimate this function. And then essentially 20 days later, another paper appeared on arXiv here, April 30, that basically also thought about the same question, whether KA architectures are useful in practice. And so they say that, well, if you're using multi-layer KA architectures, that's basically Horowitz-Mammon stuff, then you can get like very nice approximations for functions appearing in partial differential equations. Yes, it is what it is. To be honest, we were a bit upset when we noticed that they didn't cite our paper, because we are basically like talking about the same question, whether KA architecture works in practice. And like, you know, Google Scholar is right there to help people trace the references. But perhaps we should blame ourselves a little bit too, because the title of our paper doesn't really suggest we were using Kolmogorov-Arnold. At some point, we were thinking whether we should call this one factor that I'm going to talk about eventually, Kolmogorov-Arnold factor. So that would make it more explicit, but it is what it is. Okay, so enough for the like super long introduction, I guess. Once again, our main contribution is that we provide the first empirical application of KA architecture, and we show that it outperforms other state-of-the-art methods in finance. All right, model. Let's get to the very concrete stuff. We're going to talk about factor models, and I'm not sure to what extent these models are natural for the audience here. So let me spend a few minutes to motivate what we are actually doing. So we have data on returns of different assets. Let's say we have capital N assets, and we observe them for capital T months. For example, we observe them for 5 years, so that would be like 60 months, or 10 years, 120 months. For each asset I at time period T, we have the return for that asset. It could be equity, it could be stock, it could be something, doesn't really matter. And then in finance and in economics, a very popular model assumes that the returns of these assets, they can be represented through this model that has two parts, basically the common part and the idiosyncratic part. And the common part is basically governed by K factors that vary over time. So the whole dynamics of all these assets over time can be explained by these K factors, FT1 through FTK. And then assets are different in terms of how they are exposed, how do they depend on those factors. So we have this factor exposure, so as people call it, factor loadings, lambda I1, lambda IK. Okay, and so then we have this model that all the returns are governed by these factors with these exposures of factor loadings, and then there's some idiosyncratic component which is independent across time and assets. It's a very popular model, but the thing is that it's linear, right? And there's a lot of kind of attention, a lot of claims that people are doing. In particular, you can look at this Nagel book, 2021, that, well, actually in finance, nonlinearities and interactions matter. So this model may be good as a first order approximation, but we want to go much deeper. And so that's exactly what we are doing. Instead of working with a linear model, we are assuming a super general, nonlinear, non-parametric factor model, where returns again can be summarized by the common component and the idiosyncratic component. And now the common component is just some nonlinear, non-parametric unknown function of a number of factors and the number of factor loadings. Basically, factors is a things that vary over time, and factor loadings is a things that are asset specific. They're not dependent on time, but they're asset specific. And then we don't, in this model, we don't even have to have the same number of factors as the number of factor loadings. So K can be different than M. So that's a model that we want to play with. It's tough, especially given that we don't observe factors and we don't observe factor loadings. The only thing we have is the returns. And we want to estimate basically the whole structure on the right-hand side. So what we do, we apply this Schmidt-Huber version of Kolmogorov harmonic representation theorem to conclude that this multivariate function can be decomposed into a univariate function of a sum of univariate functions of original arguments. And that's very nice, because now you can notice that we get two pieces. One piece that depends only on T, does not depend on the asset I. So this becomes our factor F T tilde. And then the second piece, which does not depend on time, it only depends on the asset. So that becomes our factor loading. Lambda I tilde. The only thing is that this form is a little bit unusual, because we want this term to represent exposure to this factor. So we want to have like products rather than the sums, but that's not a big deal. Of course, we can always apply some transformation to make it a product. And that's exactly what we are doing. So let me perhaps write it down right here. So we have Q of F tilde plus lambda I tilde. And then we apply identity, we take log of exponent inside of the function Q. So we get Q of log of exponent of the sum. And then exponent of the sum, of course, is a product of exponents. And we can call this Q of log as another function. Let's call it H. It's still a univariate function. So that we get the H of exponent of F tilde times exponent lambda I tilde. And we can call like this guy our factor and this guy our factor loading. The bottom line is that what we have here, so that's exactly what I just explained, is that arbitrary nonlinear, non-parametric, non-separable factor model can be represented in this form. The return is equal to a common part and idiosyncratic part, and this common part is just some function h of the product of just one factor and one factor loading. So we don't really need all the factors. We need just one of them to summarize the whole dynamics of all the assets in this model. The only problem is that this function h is coming from Kolmogorov-Arnold representation theorem, so it can be extremely non-smooth. It is continuous, but maybe irregular. But like I said before, it's irregular on a fine resolution. Perhaps we don't care about this fine resolution. We just want to get the big picture. Like on the coarse resolution, we can approximate it by, say, low-degree polynomial. And the only question is that if it would be sufficiently good approximation for empirical purposes. At that point, when we thought about it, we were like, okay, fingers crossed, we just have to like do it and see if it works or not. So we did it, it does work, and then we are happy. Okay, so now we have the model, and let's see how we can learn the right-hand side here. Like I said, we assume that we have the returns, but we don't have anything on the right-hand side. We want to learn the whole structure, both the function h, the factor f, and factor loading, lambda I. So yes, now we get to the point of estimation of this model. The function h is continuous. It's coming from Kolmogorov-Arnold, so it has to be, by Weierstrass theorem, it can be approximated by finite degree polynomials. So that's what we are doing. We write it as a sum of two terms here, k degree polynomial and the residual. Residual disappears as you increase degree of the polynomial k.
Dennis, can I ask a question here, because it's relevant to all? We also do cons, but with Chebyshev method. So, okay. So xj here and k, capital K could be large, right?
It could be. We don't know. Yes.
So are you replacing the xj, the monomials, with Chebyshev polynomials, for example, because that will make it very nice.
I mean,
and fast, in fact.
Yes. I can't even remember how we ended up with just like regular polynomials. We didn't do any splines, wavelets, or like anything to that matter.
No, it has to do with the degeneracy, right? It has to do with the degeneracy of the basis as j goes above 3 to 4.
Oh, that's what you're talking about.
Yeah. Then you have the degeneracy, and then it's not a good representation. So
yeah, well, we can do
the
genre polynomials. Yes, they're different bases.
Yeah, just a numerical. Yeah.
I agree. In practice, perhaps you're doing actually Legendre polynomials to get rid of the numerical problems, but none of us are like experts on numerical optimization, so we are doing like naive brute force here. And also, I guess, like for finance audience, I thought it would be easier to just like write it as a straight polynomial.
I'm just saying
but yes, but I totally with you. I agree. It would be nice to rearrange them to make them orthonormal, at least with like uniform distribution. Yes, excellent. And then like we basically just assume that this guy is not there, it's just 0. And then we are minimizing sum of squared residuals, right? So this is our return. This is a predicted value, polynomial for the k with coefficients. This is factor loading, and we are minimizing the sum of squared residuals over the whole thing, over the coefficients of the polynomial, factors, and factor loadings. It's like a very high dimensional and non-convex optimization problem. So I do think we are making a heroic assumption here that we are actually able to solve it. But for theoretical purposes, we assume that we solve it in practice. Well, like we apply PCA and then do some local search and then hope that it works. Well, it does work, so that's good. But in theory, that's what we want to do. We want to solve this optimization problem. We get the factors, factor loadings, coefficient, and then that will be our estimated function. We call this estimator sieve-based least squares estimator. It's clear why it is least squares, because we are minimizing sum of squared residuals. It's clear why it is sieve-based, because we are basically using polynomial sieve to approximate continuous function. Even though we could, like you said, we could use some other sieve as well. All right, and then what do we have about this estimator? Well, we have a theorem deriving its convergence rate. So for the theorem, we need assumptions. We only need 2 assumptions here. They're not complicated, so let me talk briefly about them. So we assume that all the idiosyncratic components are basically sub-Gaussian, with sub-Gaussian norm bounded from above by some constant uniformly over all assets and time periods. It's actually a little bit a problematic assumption, because in finance people are always concerned about fat tails, but you know, in statistics the easiest results appear when you have sub-Gaussian norms bounded. So that's what we are doing here to make our life easier. And then assumption 2 is approximation properties of our polynomial sieve, right? So we say that for any k, there exists a k-degree polynomial that can approximate the original function in the sup norm, the uniform metric with this rate. That's it. These are 2 assumptions that we make. And then the theorem that we have, it shows that under these 2 assumptions, we have the convergence rate for the estimate of the main part of the returns in this mean square norm. The rate of convergence is right here. How much I want to talk about this convergence rate, I'm not sure. I mean, it's just a rate. It's relatively standard, actually. So here's approximation error, and here's the stochastic error. As long as k is not too large, smaller than the maximum of these 2 guys, if you ignore the log, basically the rate here is determined by the minimum between n and t. In finance, n and t are of the same order, so it's like the rate is essentially 1 over n, if you wish. That's a standard rate that we know from low-rank matrix recovery. By the way, we do have here a low-rank matrix recovery problem, because if we get back to our model, here's the model. If you assume that this guy is k-degree polynomial, that means that and you write this guys as a matrix n by t matrix, so that will be a matrix of rank k plus 1. So then we are really in the low rank matrix recovery literature, with the twist that single vectors of this matrix are not like totally independent. Like they're all coming from just one vector representing factors and another vector representing factor loadings. So it's a little bit more than just a low-rank matrix recovery eventually. Okay, here's the theorem. We have more results in the paper where we are concerned about like factor and factor loading themselves. So we have bounds on quantities like here and there. But I don't want to talk about that stuff because that is much more difficult and requires much more conditions. Do we have a minute? Okay, so maybe 1 minute. Actually, if you start with the original model, like we have, where is the motivation? Right. Here's a model. The representation that we arrive through Kolmogorov-Arnold is actually not unique. In particular, if you recall the original Schmidt-Huber theorem over here, you see that the order of the variables in which they appear does matter for representation. And so that means that if you take our model and just permute the factors, we'll get another representation, but the factor will be different. So estimating something which is not really identified in the model, it's tough. So that's why I don't want to talk about results and estimation of these guys. We do need to impose much more assumptions to ensure that the factor and factor loading are identified. So basically, we need to assume that the factor as a random variable has support on a closed, on a connected interval, essentially, say from 0 to 1. It should take all values from 0, 1 interval. And that comes a little bit in a clinch with Kolmogorov-Arnold representation theorem, because in Schmidt-Huber, these guys are actually taking values in counter set. So there's some, like, a lot of stuff going on if you really want to get these guys. Okay, I'm not sure if you can hear all the noise coming from the back of me, but I think that's all I wanted to talk about anyway. So there's some proofs. They are like the usual uniform entropy, uniform low Flash number types of proof in statistics. So let me just keep it and give it to Nicola.
So thank you very much. So maybe if you don't mind, I'm gonna share myself. Okay. Okay. All right. You see my slides, right?
Yes, we can see.
Okay, very good. So good afternoon, everyone. So now we sort of switch to the more finance part. So I already apologize if I take for given, things that are common in the finance literature, but maybe not common for people outside the literature. But of course, I'll do my best to be clear on these points. So as Dennis was saying before, so what is important is the performance of this empirical implementation of decay architecture. And so we take very sophisticated data, which is finance data, and try to see basically how it goes. So let me start with a preview of our result. So we estimate the model on a very large cross-section of assets. So think about equities, bonds, commodities, foreign currencies. And we use a seed-based least square estimator with a degree of 4. And what you see in this picture is the predicted average returns from our model, what the model predicts on the x-axis. And on the y-axis, you see the data, so the actual average return. And you can see that the predicted and the actual average return line up very well one with the other. This is the 45-degree line. So in fact, the R square from our model is approximately 89%. And what we also find is that if we take our model and then we take basically all the models that the state-of-the-art empirical finance literature typically use to study asset returns, so they are all subsumed by the HFL model. And so I'm going to show you, for example, some result with respect to the sort of workhorse model in empirical finance, which is the model of Fama and French, what we call the benchmark equity factor models. But we're going to also compare the HFL with the various statistical model, for example, based on PCA or on variation of the PCA. the RP PCA, where RP stands for risk premium PCA, were recently developed by Letau and Pelger. So these are adjusted exactly to explain differences in average return across assets, or kernel PCA that instead try to include the nonlinearities. And we also look at other kind of models that contain higher order of the factors, for example, square terms or interactions, and models based on factors that are constructed using macroeconomic variables. I don't know, GDP, for example. And actually, we do also something else. So over the years, the finance literature has developed many factors that have been claimed to explain returns, explain average returns. And in a very recent and nice paper, Jensen, Kelly, and Pedersen have collected all these factors together. They call it the factor zoo. And so what we do is we take these factors and one at a time, we include in our analysis together with the HFL factor. And what we find is that while the HFL factor always stays significant, most of these factors from the factor zoo, they basically are not. Only 3 out of 153 remain significant after we account for the HFL. So let me be a little bit more specific about the data. So I was telling you various asset classes. So you can see we have basically 53 equities portfolio, where a portfolio is a set of individual stocks. So these are very common assets that are studied in finance. 11 US government bonds. But we also extend the analysis to the international market. So we have 40 international government bonds. We have 21 commodities and 46 foreign currencies. FX here stands for foreign currencies. So ultimately, our samples is a very comprehensive sample of the assets that are traded in international markets. So in this sense, it's very comprehensive and very sophisticated. So in order to assess the performance of the model, we adapt to our framework a very standard empirical procedure that is used in finance that is called the two-pass procedures developed by Fama and Macbeth. And in our framework, it's very simple to adapt it. So if you can see here our HFL model that before Dennis was describing, where RIT is the return of one of these assets in month T, and there is the common component, which is given by the HFL, right? F is a time series factor, lambda I is the factor loading, and then we have this link function H, and then there is the idiosyncratic part. So we have many assets, about 170, and we have many months, okay? We have more than 20 years of data. And if we take the expectation, right, on the left and on the right-hand side, the HFL model implies that the average return on each asset is equal to the average of the HFL. And finance, empirical finance, is very much interested in exactly this object, the left-hand side. If you ever hear the expression risk premium that is commonly used in finance, is exactly the left-hand side. This is what people in finance want to explain. And so in our model, there is this simple relationship between the two. And so we can empirically test this very simply by running this linear regression, which of course implies some restrictions. And so we're going to check that this intercept alpha is 0. We're going to test whether this slope beta is equal to 1. And then we will further look at the regression R-square and the mean absolute pricing error to basically evaluate the performance of our model. So in the paper, for those of you that are interested, we have a lot of a very large amount of empirical tests here for the sake of time, and I'm going to show you just a few. And I'm going to start with the baseline results. So the first column of this table is the output basically of this linear regression here. And you see that the slope on the HFL is statistically significant. Here the 3 stars and no significance at the 1% level. And actually, if you run a test of where the null is that the slope is equal to 1, we cannot reject that null. You see that the intercept is small in magnitude and not statistically different from 0, and the R-square is about 89%. That's the number that I was giving you before. Now, suppose that we add to this regression what people typically in finance use, the factors that typically people use in those linear models that Dennis was showing you before. So, for example, the famous capital asset pricing model would include this term, the market excess return, MKTRF. You see that it's not significant anymore. So while everyone in finance use this, it's not significant, okay? Suppose you add other benchmark equity factor. This is called the size factor, the value factor. It doesn't really matter for, for today what exactly these are, but these are the factors that people commonly use in these linear factor models applied to financial data. You see that most of them are not statistically different from 0. Only this SMB, the size factor, is marginally significant, while our HFL is always statistically different from 0, not different from 1, and so on and so forth. We can also, I want to show you just one more set of results of this kind, and it's the comparison with the statistical model, with the standard PCA. These PCA that are tilted to explain exactly differences in asset returns, and then this kernel PCA, KPCA. And you see from the table that while the HFL factor is always statistically different from 0 and highly significant, none of these PCs are significant. And this is true even if we include higher order of the PCs, for example, the PC1 square or PC2 square, and so on and so forth. So in the paper, we have additional results. So for example, we control for macro factors. As I was mentioning before, we control for all these factors in the factor zoo, but I'm not going to present this here. So instead, I'm going to show you two more set of results. One is in terms of predictability. In a sense, what I've shown you so far is mostly in sample. And so we want to have a sort of assessment of the out-of-sample performance of the model. And so what we do here is the following. We take our model, the HFL model, and we see, suppose that I am an investor and I have, the HFL model with me. Can I use it to generate returns? Meaning I estimate the future returns, the predicted returns, and I make investment based on these predictions. Okay. So in particular, what we do is the following. We estimate the model. We start with the past 120 months of data on all of our assets, 171. And we use the predicted values from the model to sort the assets in different bins, in different portfolios. That's how people in finance call them. Okay. So one portfolio will contain, for example, the assets that are predicted to have in the future the larger return, and say one portfolio will contain the assets that instead are predicted to have the lowest return. So of course you want to buy the one that contains the asset predicted to perform well, and maybe you want to sell short the portfolio containing assets that are predicted to underperform. So we do this every 6 months using always the past data to basically estimate this signal that are then used to make investment decisions. And this table contains the results from this investment strategy based on the KA model. And so you see the first line, the first row, sorry, here contains the average return on each of these portfolio 1 to portfolio 5. And portfolio 5 contains the assets that are predicted to perform the best. And indeed, you see that they do perform the best. And in fact, if you buy this portfolio 5 and you maybe go short portfolio 1, you have an excess return of about 0.7% per month, which is very sizable. Now, could be that this excess return is actually just a manifestation of risks that people in the finance literature already know, but the bottom part of the table tells you that this is not the case, because we adjust this excess return. Basically we account for known risk factor. the Fama-French 3-factor, the Fama-French 5-factor. These are like the benchmark models used in empirical finance, and they cannot explain these excess returns that we find. They are all statistically significant even after accounting for this known risk factor. Now, one catch of what I'll show you is that this HFL doesn't allow you to separate easily the time series factor from the loading, in a sense that, of course, we can separate them, but we cannot really interpret them if they are not bundled all together. And we would like, to provide an idea of what this HFL is sort of capturing. And so what we do here is the following things. We look at whether our HFL is related to the exposure, the sensitivities of all these assets that are in our sample to known factors, like the equity market, for example, okay? And then so we run basically this regression, where this is the average of the HFL for the different assets. And this is a vector that contains the exposures of each of these assets to these known factors. And as you can see, so yeah, you want to look at the stars, not really at the magnitude of these coefficients. What you see is that our HFL is capturing sensitivity that factors have to known factors. So for example, the average HFL is positively related, for example, to the exposure that assets have to the movement in the overall equity market, say in the S&P 500. And so I'm going to move now to the conclusion, so maybe there is a little time for questions. So our paper provides the first empirical implementation of this K architecture. And so we propose a new nonlinear single factor asset pricing model, R equal to H F lambda plus epsilon, where the first part is the common component and the second part is the syncretic component. And theoretically, as Dennis has shown us before, we established that it can represent any non-conditional factor model, which is commonly used in finance. And we show that empirically, an estimated model with a relatively low degree of H has a superior pricing power in pricing assets across major asset classes. When I say superior, I mean with respect to all the models that state-of-the-art empirical finance commonly use. So thank you very much, and I hope that there is some questions.
Great. Thank you so much, Dennis and Nicola. This was a really great presentation. Do we have any questions from the audience?
Maybe I'll ask both Dennis and you, Nicola. One of the claims that this other paper makes is that Kans can beat MLB and so on, and we have been exploring this in the context of physical problems, and we have published paper already, and we have other work that shows that sometimes it's true, sometimes it's not. The speed is not there, and so on. But I was wondering if you tried the same parameterization with an MLP, and if you can come up with the same, because it seems that you capture that sensitivity, that one important factor, right? And then, so if you were to do this, because in some senses you change basis, right? In a different way of, would you get the same result?
I mean, it would be, if you're doing a multi-layer perceptron here, I don't think we would be able to aggregate all the factors into just one factor. So you would have to, Nicola, can you go back to the slide where?
But I have a modification, because what Nicola was showing with the kernel PCA and so on if you do, for example, an autoencoder plus an MLP, that type of, so you're in latent space, you play with dimensionality, you can learn that. Can you reduce the you know what I mean? You can massage it.
Yes.
Yeah. Because that's basically a kernel, a nonlinear projection, right? A nonlinear PCA is an autoencoder. So would you be able to do that? And you play with the dimensionality in the latent space, then that you can really also draw some conclusions from that.
There are actually papers in finance that apply autoencoder to data sets like this one, right? So you because the thing with the autoencoder is that somewhere in the middle of this neural network you will have just one neuron which you claim to be your factor. So and Nicola, can you go back to the slide where the model is defined, any one of them? And next one. Yeah, here. So autoencoder would correspond to a different representation here. We would have like no lambda, but we would have hi, if something like this. So that would be a type of model that we are considering with autoencoder essentially. People who did autoencoder in finance, they did something else. Maybe you can, Nicola, remember better what they did, but it's definitely a good idea to try. We actually thought about it, that we should probably work with things like autoencoders here on this data set and see whether we can get a nice result out of that. We didn't do it so far. That's an excellent point, I guess.
And so in some sense, the ideology of this paper, Alex, so
hi, Alex. Thanks for reaching out, because this was an excellent presentation, actually. Thanks for.
Thank you. We're also, because we're quite interested also to reaching out to machine learning community, because sort of finance lives separately to some extent. I mean, we interact, but only on the margins. But I think there's a bunch of stuff that you folks are doing, which is quite interesting. I think the ideology of this paper is actually the following. So we wanted to say, and that's why we use this one factor setup. We wanted to say, okay, the Kolmogorov node is about representation. So representation, maybe there is hope that something which is low dimensional in some broad sense, or lower dimensional than multi-layer perceptron can work. So I think that is sort of the underlying ideology and why the Kolmogorov node representation theorem is something that we were quite excited. But then we decided actually to take it even more to the extreme and say, okay, can we represent this as this one factor setting with the outer function h? In principle, h can be very, very, very complicated. You may need to have millions and billions, maybe trillions parameters to represent real sophisticated data. What was surprising for us, and that's why we're excited about our paper, is that a relatively low order approximation works. So in some sense, you can think about this as a stand-in for all of the other machine learning models that folks have used, and you can have several factors, etc. And still, this architecture would beat it. So I think maybe that's sort of the more philosophical.
I understand, and this reminds me of I don't recall if you many years ago when quasi-Monte Carlo method came out, they say, now we can solve 300-dimensional problems, and they show these Wall Street problems and 300 dimensions. Then Owens from Stanford computed the effective dimensionality of that data set, and it turned out to be 3.5.
2.5, yeah. That's about Van Neumann conjecture this.
2.8 or 3.5. So in other words, if you find the right coordinates, right? If you find the right coordinates, that could be very, very low dimensional system. It's not 300 dimensions. It's 300 dimensions because you're not in the right coordinate system. So if you find that with the mapping, somehow you find the right coordinate. And in fact, DARPA is supposed to have a new program on this topic, how you find the right coordinates, how you find the right transformation to make the problem very simple. Same thing with the Fokker-Planck. We just published a paper where we take a Fokker-Planck in 100,000 dimensions, and we do a score function. If you know what that is a gradient of the log likelihood, yeah. And then we turn that into an ODE. So I can solve with MATLAB a 100,000 dimensional Fokker-Planck. And that's the score function that is used in diffusion models now. So it's it seems what I'm saying is that this data finally they are amenable to that type, since you found it, of course, you found it empirically. But because I can try to do turbulence, for example, where you have a, yes, it's color correlated spatiotemporal chaos, but it's distributed, right? So I can have spontaneously I can have a huge range of scales appearing, and I will not be able to resolve it with this. Not with one term or a huge multi-layer can or perceptron. So that's that. But one thing we found about these cans, and I think Juan is working on it, and some other people in the lab, is that they actually have a less of a, what the spectral bias is in neural networks. They basically cannot capture high frequencies. Cans, this type of Kolmogorov representation is better, has less, let's say, less spectral bias than MLP. So that's kind of interesting. So because then said, G would be very fluctuating function, right? Continuous, but fluctuate the G. Maybe a can, this Kolmogorov representation is better than the MLP altogether. So it will be interesting to compare it with MLP. And that's what we've been doing recently in the lab, both for PDEs and also neural operators and things like that.
I mean, in some sense, there is no magic in Kolmogorov-Arnold. So Kolmogorov-Arnold just shifts the complexity of representation on the function H and on this basis function phi's. So, well, I mean, we thought, quite a long time about this. It's a long project we've been working on. But in the end, I think our take is the following. Our take is not about whether you can represent something or whether you can approximate it in something. The take is ultimately empirical or data-driven. For a given problem, what does better?
Yeah.
So for finance, we have found that this parsimonious specification works better. Maybe for turbulence, I know nothing about turbulence, but for turbulence, maybe you need to capture some very high order, very nice fluctuations.
You have to capture the Kolmogorov scale.
You have to capture the Kolmogorov scale.
Kolmogorov inertial scale, the -5 1/3 spectrum. Yeah.
so for this it may not work, but my understanding is that it's relatively easy to find examples where Kolmogorov-Arnold representation theorem can be precise. There is this beautiful book from maybe the 70s by Hovansky named Nomography. How to represent different functions via sums like Kolmogorov-Arnold sums. There, it's exact representation in a very small setting. It's how to draw these functions on the low-dimensional space. But practical question is this, I think. Can this kind of architecture, where the nonlinear outside function and nonlinear inside functions, can this do better? So we answered this affirmatively, and I think we're actually the first who did this. In terms of not just made up examples, but in terms of real data. And then what you folks are doing, I think, is also quite interesting, because you're saying for what specific physics-based problems it can outperform MLP or not.
Yeah, exactly. So we actually just put on the archive a paper on turbulence, and as one compare, we have real data on thermal convection, both temperature and velocity in turbulence. And we were able to compute statistics from experimental data, high order statistics, that you wouldn't be, very, very sparse experimental data using a can representation. We could do it also with pins or neural networks, but not as accurate, it turns out. So that was a case where there was an advantage, not huge advantage of the Kolmogorov representation, but some advantage.
And so here we show that there is, in some sense, huge advantage because it somehow is able to capture the higher order nonlinear interactions that the finance folks have not been using. So the finance folks are using the factor models, maybe interactions of the order 2, but here it's capturing higher order interactions, the 4th order and so on interactions. So here it seems that this Kolmogorov-Arnold representation is superior to at least the existing state-of-the-art class of the models. Wonderful.
So I guess the bottom line is that K-CAN it's essentially a new machine learning method, and we just need to find a class of empirical problems where it outperforms MLP, random forest, Gboosting, and whatever, right? So
and this is a right way of saying it, I think, because the MIT paper was a little bit of too much hype, and they have a lot of bugs in their GitHub and so on. There was the spline representation is totally inefficient, but people have jumped on it, and different groups, and now it's better. But their claims were a little bit of outrageous.
That's right.
Yeah.
And also, I think just more broadly, I think there was a large literature before this. We care to some extent about our work, but I think more broadly, like Horowitz and Mamin. I mean, there are a bunch of other things that people have done that it's very easy to find by simple Google search and Schmidt-Hebert, etc. That'll be nice for these folks to acknowledge as building on. But I mean, we're excited about the structure, and for maybe the folks in your lab, because we speak relatively little to this kind of community. For any of you folks who are interested in thinking, working on finance or econ applications, a large class of problems with their own peculiarities, and if you have the tools of writing this kind of models, writing them quickly, so we have infinite demand and infinite demand for this kind of stuff. An infinite supply of very interesting problems to work on. So we should definitely continue talking.
Great. Raj, do you have any comments? Raj is also working as associate professor here. He's working on CANs. Raj? You're muted. Maybe not.
Oh, maybe I have a question. One of the advantages that we have observed when we played with CANs was like they're a bit stronger to noise. Have you experimented something similar? I don't know how. Oh, my AirPods ran out of battery. Sorry about that. Have you explored something with noise, like adding some noise to your data to see what happens, like if your model, what happens?
Easy thing about finance data, it's extremely noisy to start with. There's almost no signal. If there were signal, we would be making money out of it, right? So it's like almost all noise, random walk essentially. So adding more noise, I'm not sure. We can try, but it's tough.
But I think what Juan is saying is, because we have clinical, like sterilized data, right, from simulation. So, and then we add noise to it, and we see that CANs behave well with this noisy data. In keep increasing the noise, and the response is pretty good, actually, compared to MLPs. So that was an empirical observation.
So let me answer it fun. It's actually a very good question. So let me answer slightly different. So what we do is we'll look at different asset classes, so like equity, stocks, foreign exchange, and so on. And what we know from many years of finance is that for some of these things, the factor-like models, so think about them as just projecting on some linear space where maybe these factors are some complicated things, but it's projecting on the space. For some of these things, the factor models work reasonably well. For some other things, the factor models work much less. So one of the most difficult, so to say, to price is the foreign exchange market. So Nicola is one of the major specialists on this. So, and what we were surprised is that one specification actually works across all of these asset classes, the ones with relatively more noise, the one with relatively little noise. And that is for finance application, I think is very surprising, because you can, to different degree of success, you can have the model work on individual asset class, but it's very difficult to have one parsimonious model to account for different factors. So you can think about different predictability patterns given the known methods as having different noise or different signal to noise ratio, as Dennis said. That's sort of one observation. The second observation is that something Dennis said at the very beginning. Why we think the finance data is a very high bar? Because finance data is very low signal to noise ratio. It's already very, very messy data by physics standards, etc. And having anything work on it or outperform the method people have done for many years, I think is quite remarkable.
Yeah. Right. Thank you so much, Charlie and Dennis and Nicola.
Thank you very much.
Thanks for
It was
having
a
us.
pleasure.
Yeah, it was
Wonderful. Thank you so much, George. Thank you so much.
Yeah, thank you very much. It was excellent talk.
Bye.
Have a good.
I'm glad we bridged a little bit of the gap between economics and physics.
Yeah.
Beautiful. Thanks so much, everybody.
Thank
Bye-bye.
you. Until next week.
Take care.
Hope you enjoy your week.